Thank you for coming back. So today I will present you some of the work we did here on complex systems, or what we think a complex system is. And so depending on how long we spend on each of them, we will speak about the small world phenomenon in social networks. Also speak about some cellular automata, probabilistic cellular automata, and if we have time, or very shortly, about self-assembly. So how to make sure that molecules self-assemble in the shape we want. So let's start with the small world phenomenon in social networks. So first, what do we call a social network? A social network, so you have a set of individuals, okay, and they have interactions between them. Okay, interactions can be of various kinds. It can be friends, colleagues, neighborhood, business, family, lovers, whatever. And interaction created by individual can also be web links, if it's if you consider individuals as web pages or their home pages, or they can be food chains in case of animals. They can be disease spread. How does the disease spread into a network and everything? Okay, so what do we know about social networks? We know that they can have a very large number of numbers of individuals. Okay, and an important thing is that for most of us, we don't choose our friend according to some goal. Okay, so we just have some local agreement. Basically, every interactions are local. You don't have any global agreement. You're not forced to be friend by someone else, or this is something that does not happen usually. Okay, so everything is local. Okay, you have a local view. And a usual way to present these social networks is to have one node per individual and links, connections between direct nodes, direct connections. For instance, this guy is his friend of this one, okay? But this one is a friend of a friend, okay? So you have this kind of connection. So what do social networks look like? So you have these kind of structures, okay? So here is high school dating. So blue and pink, you imagine. And so you have this kind of tree-like structures here. And here it's co-authoring. So these are the people who publish together some articles. So you have this kind of graph with. So what appears here is that you have some kind of clusters appearing, which are displayed here for each color. So whereas this one it's not clear whether it's clustered, for the other one it's fairly clear. So another example is the blog network, so the connections between blogs. So as you see again, representing such a huge graph is not an easy task, and it's hard to tell whether we can say anything from the picture. And here you have the example of disease spreading into a social network. So let's look at, so something like 40 years ago, it was really hard to get a network. Okay, now at least we can get some networks through the internet and the connections and everything, or at least private company can. And so here is an example here of a very small one that was studied in 77. It was a karate club where there was 34 members, and they had a 2 years record of relationship between the members. Okay. So you had this kind of graphs. Okay. So I don't know what the connections are. Maybe it's somebody fought against the other one. I don't know. And the thing that appears is that it looks fairly clustered. So of course, you have the colors that helps. Okay, so maybe it's just because of the colors that it appears clustered. But the interesting fact is that at some point the club split in two parts, in two clubs. Okay, and what happened here is that it did not split anywhere. It split at a minimum cut. So what is a minimum cut? minimum cut in algorithm in a graph, okay, is a cut is splitting a graph in two parts such that the number of edges that are cut is minimum. Okay, so here you see that there's some kind of structure. The structure of the graphs, you can read where the split will cut from it. Okay, you can just imagine that the structure of the graph tells you something about these three. Okay, this is not by chance that it cut here. Okay, anyway, this clearly makes sense. So what's interesting here is that basically you have two big clusters, a minimum cut, and the club split at that point. So if you look at the clustering, so it's fairly high in real networks, and especially in social networks. Okay, that's clearly usual that a friend of your friend is a friend of yours are friend. It's usually it's a fairly common property. So if you look at, for instance, for scientific collaboration, which is a specific case of friendship, what happens is that you have 12,000 authors and a clustering coefficient of 65. So do you know what the clustering coefficient is something which was statistical parameters which was invented by sociologists, and it's not clear whether it makes sense or not, but at least it tells you something on the graph structures. So okay. So why do I say that it's not sure that it makes sense? Is that you have many ways to represent the same graph, and there is no reason why this clustering coefficient, which clearly depends on the graph structure, makes sense. Okay, but clearly for social networks it makes sense in the sense that that you really know what the connections are. The graph is not arbitrary. It's not something that you pick up from nowhere. It really looks like interaction, but for me it's not clear that it's the better. We'll discuss about it later. But so what is the clustering coefficient? Is that you take a node U, okay, you look at his friends, okay, and you count the number of connections between his friends. Okay, so imagine that he has D friends. Okay, D is for degree, it's degree, or connectivity as you like. And so you would expect that the total number of, the maximum number of edges is D times D minus 1 over 2, more or less. Yes. And basically you count the number of edges between them and you call it the clustering coefficient of U. Okay. And what is the clustering coefficient of a graph? It's simply the average of the clustering coefficient of all node U. Okay? So, really, what does it do? It clearly counts more or less the number of triangles, more or less. Okay? So why it's not clear whether it's intelligent to do so, or does it really make sense? Is that basically, social networks are more or less built like a group of friends. You have basically you're part of some groups and everybody knows everybody in this group. Okay, so basically, the social network is more or less a superposition of complete graphs. Okay, it's a collection of complete graphs, and I believe this would make more sense. But of course, the problem is that computing that it's impossible. So it's very hard to compute this decomposition in groups. Okay, it's one of the hardest problems in computer science. So that's the issue. So basically, let's say that this clustering coefficient tells you something. Okay,